Okay, so we're going to analyze this. I just realized I had my microphone on the whole coffee break. Sorry. We're going to analyze this delta function potential using the field theory type picture where we have a contact interaction. And I'm doing it in at d space-time dimensions. And I have to put a mu d to the d minus 3 to keep the dimensions fixed. And now I just want to compute the scattering amplitude the way I've been doing as bubble sums. And I have to compute the bubble diagram. So I guess minus I times this is what I call B of E, the bubble diagram. And we have this is mu to the 3 minus d times integral d minus 1 q over 2 pi to the d minus 1 over E minus Q squared over M plus I epsilon. I've done the Q0 integral already. What's this? And then this, if you use your dimensional regularization formulas, is minus M outside, minus M E minus I epsilon to the D minus 3 over 2 times the gamma function 3 minus D over 2 times mu to the 3 minus D over 4 pi to the D minus 1 over 2. And as D goes to 3, because that's the space-time dimension, so that's 2 spatial dimensions. This goes to M over 2 pi, and now I get a pole from the gamma function because its argument vanishes. So there's a 1 over D minus 3 pole plus M over 4 pi times gamma, the Euler gamma constant, log 4 pi plus log of k squared over mu squared minus I pi plus order D minus 3, which vanishes. And so your scattering amplitude, which is equal to 1 over minus 1 over C naught plus B of E, is equal to minus 1 over C naught plus M over 2 pi, 1 over D minus 3 plus M over 4 pi times the stuff, gamma minus log 4 pi plus log k squared over mu squared plus order D minus 3. All this to the minus 1. And the relationship between, this gets nicer if I define C naught is defined to be G times 4 pi over M. So this is just going to be a definition. It neatens up the factors. And so you find then that A be written as 4 pi over M, 1 over minus 1 over G, minus 2 over D minus 3, plus gamma E, minus log 4 pi, plus log k squared over mu squared, minus I pi. And so the MS bar prescription is that minus that 1 over G is equal to 1 over G renormalized of mu plus where do I have this line here? to be minus 2 over d minus 3 plus gamma e minus log 4 pi. So MS would say subtract off the pole term. MS bar says also subtract off this junk. That's just a convention of finite subtraction. Go ahead. I'm sorry? If I made some sign errors, I'll have to go back. This should be a plus. Yeah, this should be a plus, that's right, because I had a plus here. Okay, fine. Yeah, there's a mistake in one of my lines here. But are you okay now? Yeah, okay. It won't matter because I'm going to subtract it. It's the log that matters. Okay, and therefore your scattering amplitude is equal to 4 pi over m times minus 1 over g renormalized of mu plus log a squared over mu squared minus I pi. I'm sorry. Okay, so if I define mu d g bar of mu, I'm going to drop the r for renormalize d mu equals beta of g bar. Well, sorry, you should, first of all, the amplitude has to be physical. Therefore, mu d by d mu of minus 1 over g bar of mu plus log a squared over mu squared must be 0, because this mu dependence has to be soaked up by that because the amplitude can't depend on it. From that, we get an equation for the beta function, which is that this is equal to 2 g bar of mu squared. Therefore, you can write g bar of mu. You can solve this differential equation. Has to equal 1 over some g naught evaluated at a scale mu naught. And therefore, g bar blows up at a scale mu equals mu naught times times e to the 1 over 2 g naught bar, 2 g naught. Now, so if I do some experiment at mu naught, that's my energy scale, and I measure g naught, then g bar is going to blow up at this scale. If g naught is positive, then and small, then this is a huge scale. It blows up in the UV. So if it's positive and small, then mu is much, much greater than mu naught. If g naught is negative and small, then mu is much less than mu naught. So if it's a repulsive interaction, this corresponds to repulsive. It blows up in the UV. And we have a theory like that, which is called QED. And this is this scale where it blows up is called the Landau pole. In QED, charges get screened in the IR, they get weaker in the IR, which means they get stronger in the UV. As you get closer and closer, as you probe closer to the electron, you pierce its shielding and you see a bigger and bigger charge until finally it looks infinite when you hit the Landau pole. But if it's attractive, you have what's called asymptotic freedom. Namely, that the coupling goes to 0 in the UV and it becomes strong in the IR. So if you instead scale, this arbitrary scale mu naught, define u equals lambda equals the scale where it blows up, then what you find is that g bar of mu is equal to 1 over log of lambda squared over mu squared. Sorry, that's for it's like this is for attraction. As mu gets bigger than lambda, then this is a negative number, and then the G naught is negative. The G bar is negative. Okay, and then finally, you can relate this to delta for the square well. The same phenomena happens where you find, you do the same calculation, you find that this is equal to the scale minus J naught of alpha over alpha J1 of alpha minus gamma E for delta. So you see that it's exponentially different than the size of the square well. So this is an example where at weak coupling, you get you get knocked off scale invariance by a small amount. And if it's a positive coupling, it gets knocked into the irrelevant side and becomes weaker very slowly in the infrared. And if it's attractive, it gets knocked into the relevant side and it becomes very important at low energy. Now, of course, you cannot trust that the coupling actually blows up at mu equals lambda, because at that point, G becomes large and non-perturbative. Well, in this example, you can, but in QCD, you can't, because there are all sorts of diagrams that you didn't include in computing the beta function. Here we included all the diagrams, so it's valid. So later, I'll show you that this is what happens in BCS theory. But right now, I want to switch to a famous asymptotically free theory, which is QCD. I went to a conference in Vietnam last summer, and my hotel room had a brass plaque outside it that said, "David Gross slept here." So the next time I saw David, I said, "Hey, I slept in your bed." He said, "What?" Hmm? I'm sorry? Yeah, David Gross, discoverer of asymptotic freedom. Gross-Molitor-Wilczek, yeah. Oh, I also have I also have to tell you an anecdote, which was told to me by Tom Applequist, who was an assistant professor at Harvard in the early 70s. And he and a postdoc had decided that non-abelian gauge theories had just been shown by TOEFL to be renormalizable theories that you could calculate things in. And so they decided that the beta function had been computed for all other theories, Yukawa theories, 5/4, so on, but, and QED, but no one had computed the beta function for non-abelian gauge theories, so they decided they wanted to do it. And they got about 50 pages of calculations and decided that it was a mess and that it was going to depend on the gauge fixing parameter. And therefore, it couldn't be physical. And so they said, we don't want to do this hard calculation just to get to some non-physical answer. And so they decided to quit. And David Politzer, who was a graduate student, walked into the office and said, I'm calculating the same thing. And they said, but it'll be unphysical. And he said, I'll just do it and see what I get. And so he got a Nobel Prize. And so this is a lesson. As you get older, you start feeling like a problem isn't worth your time. You do a cost-benefit analysis. You've seen 99 out of 100 projects fail, and you think, oh my God, this is gonna be another 2 weeks, and then it's gonna fail again like all the other projects. So you start getting cautious, okay? And that's why young people do make the great discoveries, because they aren't cautious, they are optimistic, and they jump into things. And so you should guard your optimism. Don't let age and disappointment wear you down. So QCD gets wrong in the IR, and that explains all sorts of phenomena that people were baffled about in the early days of the strong interactions. And in particular, one amazing phenomena that was discovered by Nambu is he was very intrigued by BCS, which for quantum field theorists is sort of the biggest theory of the 20th century. It showed that the vacuum could be very complicated and non-trivial, and nobody had ever thought that before. Everybody thought that the vacuum was a bunch of harmonic oscillators wiggling on their 0-point motion and not interesting. But they showed that the vacuum could rearrange completely and cause Cooper pair condensation. And Nambu just said, well, maybe that could happen in a relativistic theory. And he did a completely unjustified calculation with horrible approximations to the NJL model, and came up with some really interesting phenomena, which is that if with these unjustified approximations in strong coupling, you find that you could get psi bar psi condensation in the vacuum if the fermions were strongly coupled. And when you look at that paper and you realize this was like a decade before QCD was written down, okay? And quarks were a quark model. They weren't real quarks, and there was no idea of color. This paper is just genius. How he figured it out is unfathomable. But anyway, the reason why he was interested in it was because another thing was happening at that time, which is people were understanding what happens when symmetries get broken. In particular, when global symmetries get broken, you get Goldstone bosons. And he said, if this happens, it will, if you write this in terms of left and right-handed components, it looks like this. And so these condensates marry the left and right parts of the fermions together, and therefore you do not have symmetry where you can independently change their phase, which is called a chiral symmetry. If you have a free fermion with no mass term, you can write this as psi bar left plus psi bar right, p slash psi right, where psi bar left or right is a projection operator, p left or right, acting on psi, where this is 1 minus or plus gamma 5 over 2. And you project out the different chiral components. And therefore, it's obvious in this form that this kinetic term has independent phase rotations for the left and the right. And that gets broken when you have a condensate which marries the two. And Nambu knew that when you break a global symmetry, you get light bosons. And therefore, he said, this could explain why the pions are light. namely M pi much less than M nucleon, which was a mystery. Now, one thing I'd like to emphasize, and when you want to write dry, so what we're going to do is we're going to come up with a theory of these pions as Goldstone bosons called chiral perturbation theory. And one thing I want to emphasize is that when you spontaneously break a symmetry, the symmetry is still there, okay? A symmetry, there is some Q which commutes to the Hamiltonian. Q is the generator of the symmetry. Namely, if I define U equals e to the I theta Q, then psi goes to U psi U dagger is the symmetry of the Lagrangian. Now, this makes no reference to ground states, right? So it's true no matter what your ground state is. I mean, if your Hamiltonian obeys that in the high energy theory, it obeys in the low energy theory. So if you have a symmetry of QCD, and then you get confinement and chiral symmetry breaking, it doesn't matter that the symmetry is broken by the vacuum. It's still a symmetry in the low energy theory. And that seems sort of weird because, and I will illustrate it in a way that's really easy to understand what's going on, even though it sounds like it's going to be a very complicated example, which is I'm going to not talk about the spontaneously broken continuous symmetry, but spontaneously broken supersymmetry. The reason why it's so simple to understand is because supersymmetry says that you've got Bose states and you've got fermion states, and they come exactly paired in energy, except for possibly a ground state, which is Bose, and with no fermion counterpart. Now you spontaneously break supersymmetry. So for example, here, what you find is that the mass of the electron would equal the mass of the selectron, its supersymmetric partner. Obviously, it does not look like the real world. Supersymmetry has been called the ultimate unified field theory because it unifies every known particle to an unknown one. When you spontaneously break supersymmetry, you can have M electron equals 0.511 MeV, and M selectron equals 1 TeV. So what in the world, how in the world do you say that the symmetry is still there? Because after all, if you know group theory, there's Schur's lemma that says that if you've got some generators and they commute the Hamiltonian has to come in degenerate blocks proportional to the identity matrix, which says that all the states in a multiplet have to be degenerate. So the symmetry says there has to be a degenerate state, which is its supersymmetric partner at 0.511 MeV. Well, the way around it is this Hamiltonian is not just a one-body operator. It involves all possible states. So the way spontaneously broken supersymmetry does this is that you have a fermion state, which is your electron, and you have a Bose state, which is an electron plus a Goldstino. There has to be a massless fermion in the theory so that you can put a zero momentum massless fermion in addition to your electron to make a degenerate state. So the existence of a massless Goldstino is mandated by the fact that you have to have a state that's degenerate with the electron. And the only way to do, and it has to be boson. So the only way you can do it in a two-body state is to add a massless fermion. So that's where the Goldstone theorem works for supersymmetry, and it's clear because you have to have this degeneracy. With continuous symmetries, it's less obvious because you can add a massless pion, you can add 2 massless pions, you can add 10 massless pions, so it's harder to make this argument, but the massless pions are there for the same reason, which is that the full chiral multiplets are made up by baryons plus massless pions. The massless pion has to live in the theory to make the low energy theory symmetric, while still having non-degeneracy between the multiplets. So we call this non-linearly realized symmetry. But what it just means is that you're filling out the multiplets by adding massless particles. So let's look at QCD with so you have a sum over flavors, U, D, S, C, E, T, Q bar I, D slash Q I, minus Q bar I, M, I, Q I, and then glue on stuff. So this by itself, Q bar I left, D slash Q I left, plus Q bar I right, D slash Q I right. This has an SUNF left symmetry. The left just tells me it's acting on Q lefts. It actually has a UNF, and this has a UNF, which I'll call UNF right symmetry. This term violates it because this is equal to Q bar I left M Q I right plus Q bar. And what I'll do now is I'll pretend that M is, this is a mass matrix, which is diagonal. I'll pretend that it is complex. I mean, I'll allow for it to be complex. So now what happens is that if you make this transformation, Q goes to LQ. I'm dropping the flavor indices. This is a UNFL transformation. And so this is Q left, sorry. And Q right goes to Q right. R times Q right. Then your Lagrangian goes to Q bar E slash Q, that's not changed, but you get a plus a Q bar left L dagger M R Q. Let me call this M dagger and this M. So plus M dagger L dagger M dagger R Q right plus Q bar right R dagger M L Q left. And so this is not a symmetry of the Lagrangian. But not all masses are the same. Top and charm and bottom are very big compared to lambda QCD. Up and down are very small compared to lambda QCD. Strange is sort of in the middle. So latest lattice data, MS is about 100 MeV. MD is about 5 MeV. MD is about 2.5 MeV. And I don't know, M charm is about what, 1.5 Jeb? So lambda QCD is somewhere around here where the QCD theory gets strong. And so these are light. This is sort of light. And then everything up here will be heavy because the measure of how badly the symmetry is broken, that's a dimensional parameter. We have to compare it to something. And it turns out that lambda QCD is sort of the right scale, maybe a GeV. I don't mean necessarily it has to be 200 MeV, but maybe it's 1 GeV, something like that. And so for the light quarks, and up and down, certainly maybe S, this is a small deviation, small symmetry breaking. And so we might hope that we can do perturbation theory in the small masses and around the case where there was an exact symmetry and do perturbation theory in the masses. Now, these are unitary symmetries, which are special unitary symmetries times U1s. One combination of U1s is baryon number. That's completely unaffected by this condensate. This condensate doesn't break baryon number. Psi and psi bar have the equal and opposite phase rotations invariant. So we can forget about baryon number. It's going to be conserved. If you ever want to do grand unified theories, you have to rethink that. But for QCD, it's conserved. And then the U1 axial is a long story. You probably heard it, but anomalies, the QCD anomaly breaks U1 axial, and for the purposes of my lectures, it's just not a symmetry. It's broken by things that you don't see when you look at the Lagrange. So we're going to deal with just the SUN cross SUN symmetry. And so if we take just these two, this is U, sorry, then we have SU2 cross SU2. Or if we take this one, it's SU3 cross SU3. And that's the symmetry of QCD, and it's approximate because it's broken by the masses. But then it's spontaneously broken by the condensate. So this would go to Q bar, let me write this as, let me write Q bar R J Q L I. We're saying that this is going to be some scale, I don't know what it is, delta IJ. I mean, it's on the order of the strong scale. And under SUN cross SUN, this becomes, well, this gets multiplied by L, which attaches to the I index. So this becomes lambda squared. And then I have a lambda cubed, sorry, times L. And then this is the unit matrix. And then Q bar right gets multiplied on the right side by an R dagger. And so this turns into the matrix multiplication of L R dagger. So what part of SUN cross SUN is broken? Well, notice that if L equals R equals V, which is, these are SUN matrices, so I lock them together, then in this case, LR dagger is equal to VV dagger equals 1, and I haven't changed the ground state at all. So in this matrix language, this is lambda cubed times the unit matrix. So I get back the unit matrix. And so there's an SUN subgroup where the left and right are locked together, which is unbroken. So this is called the vector SUN. So if I just consider the light two fermions, SU2 right cross SU2, SU2 left cross SU2 right gets broken to SU2 vector, and that has another name, which is SU2 isospin. I usually use an I, but it's the same as T in Daniel's lectures. Or you have, if you want to live dangerously and consider the strange quark to be light, it breaks to an SU3 vector, and this is called SU3 Galman. So now, by Goldson's theorem, we're going to get a Goldson boson for every broken generator. So all you do is count the number of generators here, 3 plus 3, and subtract off the number that aren't broken, 3, and you're left with 3. So this would have 3 Goldson bosons, which are the pi, plus, minus, and 0. Or 8 plus 8 minus 8, you get 8 Goldson bosons, which the pseudoscalar octet. Which on a diagram of isospin versus hypercharge. You've got your K plus, your K0, your pi plus, pi 0, and eta, and pi minus, and then your K minus, K0 bar. How do we write down, so we have a natural hierarchy. If the quark masses are 0, these would be massless particles. So there's a gap between their masses and all the other hadrons, which start at the rho, the omega, the nucleons, so on. So there's a region there where we can do physics, where we can make it an effective theory of just the Goldstone bosons. So how do we construct it? We don't know anything about the wave function of the pion. We can't solve a Schrodinger equation. So the guidance is we make sure that the low energy theory has the same symmetries as the high energy theory, and we write down the most general theory we can with those symmetries. And those symmetries are not just the symmetries that are unbroken by the vacuum, but the full symmetries. The full SU2 cross SU2 or SU3 cross SU3, because they are non-linearly realized, but they're still there. So to figure out what the low energy, the first thing you have to do is, what are your fields, you know? So this is very easy to picture because we can make an analogy with, let's imagine we had a magnet that magnetized suddenly and chose a direction. It's a two-dimensional magnet. So now the spins could all rotate this way and have exactly the same energy. They, by chance, chose this direction, but they could have chosen any other direction. They're all degenerate. That means that that if we did a rotation over a very large region, it shouldn't cost much energy, because if we do a rotation over the entire universe, it costs no energy. A rotation over a small region costs energy because there's some mismatch of the arrows over a region. They want to be lined up and they can't be. But as the wavelength of your disturbance gets longer and longer, the arrows are very well aligned the whole way. And so the energy goes down and down and down as you make the wavelength of your disturbance longer and longer. So here the analog of so in that case, the broken symmetry is rotation. And the rule is, why don't we look at excitations where we look at rotations that are localized, but over very long distances, or in other words, long wavelength rotations, spin waves. So we ask, well, what are the spin waves here? Well, we just have to promote L and R to be X-dependent rotations. That is not a symmetry of the Lagrangian, but the argument is that as as the wavelength gets longer and longer and they become more and more constant, they are symmetries of the Lagrangian. Not symmetries of the ground state, but symmetries of the Lagrangian. So that means we're going to look at an excitation above the ground state. It look like lambda cubed L of X, R dagger of X. We're going to take this Q bar Q condensate and we're going to deform it away from the ground state. The ground state is something like that. This is a new ground state, which has the same energy as the old ground state. Now we have an excitation because these are not constant. And there's no reason to distinguish between L and R. I can call this sigma of X. But it's a unitary matrix, especially unitary. And that's going to be my field. Now, we're not used to working with fields that are unitary matrices. So what we can always do is we can rewrite sigma of X is equal to e to the, and I'm going to be slightly perverse here. I'm going to normalize it in a special way. Right. I'm going to say it's e to the 2I pi over f over f, where this pi is a matrix field. It's sum on A times pi A of x times the generators TA so for n equals 2, pi is equal to the sum of the Pauli matrices over 2. Those are your generators. I'm normalizing these to be trace TA, TB equals a half, delta AB. That's my convention. So that's Pauli matrices over 2 times pi I of x. And that's just a matrix, pi 3 over 2. I'm dropping the x dependence here for minus pi 3 over 2, pi 1 over 2 minus I pi 2 over 2, and pi 1 plus I pi 2 over 2. These are 3 different fields. They're going to be our pions. They're functions of x, and I'm exponentiating them. But what are the rules for how do I, well, first of all, how to identify which of those pi 1, 2, 3s are which pions? So to understand that, we have to understand how does sigma transform under our SU2 cross SU2 symmetry. We're taking Q bar right I, Q left J of X, looks like sigma of X by J. That's our excitation above the ground state. Now, under SUN cross SUN, the exact symmetry of QCD, how does this transform? Well, we just multiply this by a constant L and this by a constant R dagger. So that goes to L sigma of X R dagger IJ. So if I took my whole box with its spin wave excitation and rotated it, it should still have the same energy. So that's what we're doing here. We're saying this is the spin wave above the vacuum, and I'm taking the whole world and rotating it in some complicated way by the symmetry of QCD. That should be, my theory of sigma should be invariant under that symmetry. That's going to be the task. Write down the most general theory invariant under that symmetry. Now we can use this to understand how the pions transform under the symmetry that wasn't broken. Because remember, the nonlinearly realized symmetries are not evident when we look at the one particle spectrum. But the linearly realized ones, the unbroken symmetries, are. So every particle should fall into a multiplet of this SUN vector symmetry, which for n equals 2 is isospin. So our pions should be identified by isospin. So if we look at the vector subgroup, remember that we got by just setting L and R to the same unitary matrix. Sigma goes to V sigma V dagger. Now, that's equal to V e to the 2I pi matrix over F times V dagger. And if I expanded this exponential in a Taylor series, you'd see I could stick a VV dagger between every pi matrix, because VV dagger is 1. And that would have let me prove that this is actually equal to e to the 2I over F V pi V dagger. That makes sense? And so we can say that the pions under the transform nicely under the unbroken SUN symmetry, which is like that. So for n equals 2, isospin pi goes to V pi V dagger. Now, V is equal to some set of angles times rotations, where this is SU2 generators. And so under an infinitesimal isospin rotation, we have delta pi looks like the commutator of TA with pi, because this looks like 1 plus I theta dot t. And this looks like 1 minus I theta dot t. So if I expand a linear order and I theta, I'm left with this commutator. And so I could just read off now. So for example, if I take A equals 3, I look at T3 commuted with pi, which is 1/2 minus 1/2 commuted with a 2x2 matrix. This term here is going to get a 1/2 when multiplied from the left. And on the second part of the commutator, it gets multiplied by a minus 1/2, but with the minus sign from the commutator. This picks up a, sorry, I'm sorry. This one here gets a plus 1/2 on one side of the commutator, but it also gets a plus 1/2 from the other part of the commutator. And so when it commutes with this, and I get a 0. So whatever we're in the 2x2 matrix, this gets multiplied by 0, this gets multiplied by 0. This one here gets a 1/2 from the first part of the commutator and a minus 1/2 from the other side. So this is plus 1. This one gets a minus 1. And so you see then that when I write this as pi 3 over 2 minus pi 3 over 2, pi 1 minus I pi 2 over 2, and pi 1 plus I pi 2 over 2, that this picks up 0. It has isospin I3 equals 0. So this guy must be our pi 0 because it's got isospin 0. And this picks up a charge 1, so this must be our pi plus, because that is isospin plus 1, and this must be our pi minus. So now, the only question is, how do we normalize it? So for example, if I look at trace d pi, well, if you do conventional normalization, what you do is you say that pi 1 minus I pi 2 minus plus over root 2 is pi plus minus, and pi 3 is equal to pi let me get this right. What did I do wrong? Sorry. Say it again? Pi 0. Yeah, what am I getting? Right, okay, so that means that our pi to be written as 1 over root 2 times pi 0 over root 2 minus pi 0 over root 2, pi plus, pi minus. So we've identified which particle is which. We've identified the symmetry that the Lagrangian has to be invariant under. So now let's write it down, the first term at least. So you say, oh, that's simple. I'll write something invariant, which is trace sigma dagger sigma. But sigma is a unitary matrix, especially unitary matrix. This is equal to 2. That's not very exciting to put in your Lagrangian. It's the cosmological constant. If you had a theory for that, that would be exciting, but it's not very useful for our theory of pions. So the lowest order thing you can see has to have derivatives, because there's no operator you can write down without derivatives. It isn't trivial. So right away you understand why Gulfs and bosons are always derivatively coupled. If you don't put derivatives in, the sigmas and sigma daggers just collapse into numbers. So now I have to put something out in front, and this is going to give us our kinetic term for the pions when I expand this to order pi squared. And so it's nice to have the conventionally normalized kinetic term. So it turns out that f squared over 4 will do that. So this will give us 1/2 d pi 0 squared plus d pi minus. You can see where the funny root 2, why there's a root 2 for the, I erase it. The relative root 2 that appears for the real scalar for the pi 0 versus the charged ones which don't have the root 2s because the kinetic term looks like this for a complex scalar field and has the half for the real one. And then you get a whole bunch of interactions for free that are required by this non-linearly realized symmetry. So if you expand, you get the next term, which is going to look like 1 over 3 f squared trace of the commutator of the derivative of the pi matrix with respect to x mu commuted with the pi matrix squared. And that gives you a 4 pion vertex with 2 derivatives in it. And so now you have a prediction for pi-pi scattering. And Weinberg realized that and gave the first calculation of the scattering length for pi-pi scattering. He didn't use this parameterization, he used a really terrible one, but it worked fine. Now, the problem is this involves an unknown quantity, f. How do we fix f? So that's where I'm going to have to do that and then quit today. So to fix f, you use the fact that we don't know anything really about QCD dynamics, other than now we have the lattice, of course, we can do numerical computations, but very little theoretical understanding about the dynamics of the quarks inside these objects, but we have a good understanding of symmetries. So one thing we know is that in the weak interactions that are responsible for pion decay. And it comes from an operator that looks like 1 over root 2 G Fermi times VUD times U bar gamma mu 1 minus gamma 5 times D times leptonic current gamma mu 1 minus gamma 5 times nu mu. Now, we know, sorry, too many mu's here. Let me put a nu here. Oh, too many news. Shouldn't name particles after indices. Okay, so this is the lepton current. We can just stick in our U and V spinners for those guys. They're weakly coupled, easy to deal with. This thing we don't understand. How does this interact with the pion? Well, the cool thing is we do understand it because this is 1 minus gamma 5 over 2 is P left. And therefore, this is proportional to Q bar left gamma lambda times 0, 1, 0, 0, where this is in flavor space, where Q is up and down. And this current is one of the generators. It's a linear combination of this thing here is sigma 1 plus I sigma 2 over 2. And so this is a linear combination of, oh, sorry, this isn't right, this is left. of SU2 left currents and we know how to compute SU2 left currents in our Cairo-Lagrangian because we know how the particles transform under SU2 left and we know Noether's theorem. So if you want to know how this matches on into the effective theory, you just have to replace the left-handed current of the quarks by the left-handed current you compute in your effective theory. That's the transformation under SU2 left. Use Noether's theorem. And what you find is that JMU left A is equal to minus I F squared over 2 trace TA sigma dagger d mu sigma, which if you expand it is F trace TA d mu pi matrix plus order pi squared. I know how to take the matrix element of this operator between the vacuum and the pion because there's a pion field in it. And it will give me a factor of the momentum. And so what I find is that, that I can compute this matrix element. And when you do that, this is defined to be, so if you define the matrix element between a pi, between the vacuum, the current, U bar, gamma mu, 1 minus gamma 5, D, active, and a pi minus field with momentum P. If you define this to be I square root of 2 F pi times P mu, then you can compute this in the effective theory and you find that F pi, that F equals F pi, which is why I called it F. And you experimentally, this F pi is 93 MeV. And you'll find that different authors have different conventions. Some people lump this together and call this F pi, which is then 130 something MeV. So you have to be careful to find out which F pi they're using. So this is crazy. We use the weak interactions to fit the one unknown coupling constant we had in this low energy theory, which is F. And once you do that, you've got all these pion interactions to very high orders. But of course, there are higher order derivative terms I can write down. Operators with 2 derivatives, 4 derivatives, 6 derivatives, and so on. They'll be there, but they're not very important at low energy. So we have a momentum expansion for pion physics. And it's not like the nuclear physics. It's not non-perturbative. You can just do it as a power expansion in P's over F pi's. What we'll have to do at the beginning of the next lecture, or maybe you'll hear it from Professor Isidore, that we haven't put in the quark mass matrix. And we'll be able to do that because we'll remember that in QCD, we had Q bar left M dagger Q right plus Q bar right M Q left. And so under the transformation, this goes to Q bar L, let me just look at this one here. This goes to Q bar right R dagger M L Q left. And so we can say, well, QCD would have been invariant if M also went like M goes to R, M, L dagger. So if we pretend that M transforms like a dynamical field, then the theory would be SUN cross SUN invariant. So the same thing must be true in the effective theory. We can put an M where if we transformed M like this, it would be invariant. And so then it's clear that since sigma goes to L sigma R dagger, we can immediately write down trace M sigma plus Hermitian conjugate as an operator. And then with some coefficient, this only has dimension mass. We have to have 3 more powers of mass out here to make it fit in a Lagrangian. We don't know what they are, but we can then compute from this the masses of the mesons in terms of the unknown coefficient. And miraculously, there are 3 unknown coefficients for 4 masses in the isospin limit for SU3. Sorry, for SU3, there with isospin, there are 4 different types of mesons. There's the pions, the kaons, and the eta, that's up to 3. I'm sorry? Right. There's the K plus, K minus, and then there's the K0, K0 bar. And no, I'm mixing stuff up. But why am I having a mental breakdown here? Hang on a second. Sorry, you've got 3 masses, the pion mass, the eta mass, and the kaon mass, and you have 2 free parameters in the theory, it turns out. And from that, you can make 1 mass prediction. That's the Galmano-Kubo formula, which works to within 1%. So we'll talk about that next time, or perhaps you'll hear it or then in the next lectures. Thank you.
So you start with the SU3L cross SU3R symmetry for writing the terms, like in terms of sigma. And but finally you have like SU3L cross SU3R broken to SU3V. So when you write terms with sigma like the operators, do you consider that it has to be invariant under only SU3V or full SU3L cross SU3R?
Can you repeat? I couldn't hear.
So when you write the octet, do you demand that the octet be the potential should respect only the vectorial part of SU3 cross SU3 or the full?
So when I say that sigma goes like L sigma R dagger, this is the full SUN cross SUN symmetry, not just the vector symmetry.
Yes.
So the theory is invariant under the full symmetry, not just the vector one, right?
Right. But when you're looking at the terms, like because sigma is under SU3V, it's like an adjoint, but under SU3L cross SU3R, it's like bitriplet. So,
sorry, when it goes to the microphone, I just can't pick it up.
Sigma is adjoint under SU3P, but it's a bifundamental under SU3L cross SU3R.
Yeah.
Yes. Continue. So then the writing sigma, if I take it as adjoint, its form would be some like symmetric 3x3 matrix. But if I think of it as a bifundamental, I can make it more general.
You don't have to think about sigma. You can think about the pions. Okay. So I've got some 3 angles here for this SU2. I've got 3 different angles for that SU2. This will give me a new SU2 matrix, function of X, right? I can, in principle, take the log of that and compute what the new pion fields are. What you find is that when you do a vector symmetry, as I showed you, they transform linearly, that the pions mix up with each other linearly. When you take the L and R dagger, not L and R not to be the same matrix, they transform non-linearly. The pion goes to pion plus pi's cube plus pi fifth plus pi sixth. It's a nasty, horrible transformation, but it's a symmetry of the theory. And this is why we write the theory in terms of sigma instead of the pions. You'd never in a million years guess how to write down interactions in terms of the pions, which are invariant, because you need an infinite number of interactions to make it invariant. And that's why it's called a non-linearly realized symmetry, because, and also, by the way, there's a moral there that because it's nonlinear, since you find under, if I take L equals R dagger equals e to the I alpha dot sigma over 2, then I find that the pions go to pi plus pi cube plus pi fifth plus da 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 with alpha dependent coefficients. These are functions of x. It's local. But if I did a Fourier transform, you know that the Fourier transform of pi cubed is a convolution, right? Involves all different momenta. So if you try to do calculate loop diagrams in this theory with a momentum cutoff, where I say pions with momentum less than lambda exist and pions with momentum greater than lambda don't, you would break the symmetry. And so you can see from this that you would better not use a momentum cutoff because you'll break the symmetry that you'll be choosing a regulator that breaks the symmetry, and then all hell breaks loose. So this nonlinear realization, by the way, tells you that you're going to probably need dim reg or something like that in order to, unless you want a lot of trouble. Sorry, didn't get further.
Couldn't be better.
Good.
Yeah, for the masses, so if you do in the ISOSP limit, you have two masses and so two quark masses and three. You can do in S3, you have three masses and then you have to three plus.
Yeah, I've done it, but you know, when you're at the blackboard, sometimes you get scrambled up. Nope, I did it off.